So this is the second calculation video, and in this particular video there's going to be a real concentration on practical techniques, empirical formula determination, reacting mass reactions where we're changing mass, or titration questions where, especially back titrations, we're going to look at those. So a typical waters of crystallization question. This one's been nice and given us a diagram, but the main information is that you're given 3 masses, and so the difficulty here can be working out which things to take away from what to work out the masses involved for the empirical formula of this salt. So really I want to know what's the mass of water and what's the mass of sodium carbonate. So if I just do a very quick sketch of an empty crucible and put the mass underneath, then I'm going to draw the crucible with the hydrated salt and put the mass underneath that. I'm heating it to remove water, so I'm just showing myself a little kind of reminder that that's what's happening. I'm trying to show less solid in the final bit, and then I've got the mass of the final solid, and I'm writing down Na2CO3 to remind me there's no water there now. So what that shows me is if I do 24.92 take 25.47, that's the water, because that's what was lost during this practical. And if I do 24.92 take away 24.35, that's the sodium carbonate. Other examples? Maybe we're going to do something like heating magnesium in oxygen. So it's going to gain oxygen from the air, and the mass of the solid is going to increase because we're adding oxygen to make magnesium oxide. More of a GCSE practical, but similar things could come up. They don't have to be as simple as this reaction. The important thing is I'm just visualizing that's the mass of the empty crucible, that's the solid, that's the mass at the end. It just makes it easier to work out which mass to take away from which. You might not need to do this, but it sometimes helps as you're going through, certainly the more challenging ones. Decomposition of a carbonate is another very key one where you're asked to calculate the difference in mass. So here I've just kind of visualized the carbon dioxide coming off as a gas, as mass being lost in the reaction, hence why the mass has gone down at the end. I could work out the final mass because I've got my empty test tube written down. They don't have to be good drawings, as you can see. They're pretty terrible, but drawing really does help our brain process things. So here's something a little bit more challenging. Now we've got multiple different chemicals involved. We've got a much more challenging chemical equation, although actually I don't need all the information. We've got a volume and concentration of sodium hydroxide that the ammonium sulfate's been added to. Then later on in the question, we're doing something else and we're adding sodium hydroxide. So working with what we've got, I'm just going to write down the volume and concentration of the sodium hydroxide that this original sample was added to. So in goes some ammonium sulfate. I haven't bothered drawing it as a solid. It says a sample, I'm going to assume it's a solid because it's not given me a volume or a concentration. So that's gone in. That reaction at the top has happened. And it says an excess of sodium hydroxide was used. So there is now going to be sodium hydroxide left over in that beaker. I'm going to make a note that some ammonia gas has been made. So if the question wanted me to calculate volume of ammonia gas, I've written down the kind of relationship. And I'm also going to definitely write down that it's 2 moles of sodium hydroxide to 1 mole of ammonium sulfate. Going to need to use that in any calculation I do involving sodium hydroxide. So this whole sample from the beaker was then transferred into a flask, because it then says it doesn't say it's going to be titrated, but it says it required 27.3 centimetre cubed of 0.6 moles per dm cubed acid. Well, with a nice accurate volume like 27.3, that came from a burette, definitely. So we've ended with a titration. And that was HCl. So This is like a back titration. Basically, I'm going to use the moles of HCl to work out the moles of sodium hydroxide and then the ammonium sulfate. All I need to know in terms of that equation is that it's a 1-to-1 ratio. I haven't written the whole thing out. I know it's 1-to-1 because 1H plus and 1OH minus come together to make water. So that is a balanced equation already. Like, I don't need to put any numbers in front. So working with this, I've actually not put the full question in, but let's say that the question wanted to know the mass of ammonium sulfate in the original sample. That's quite common because we often want to do percentage by mass. So once I've kind of sketched out what's happening, I'm going to work backwards. So I'm going to work with the last bits of information I was given in the question. And because that's the only thing I can do anything with, because it's the only thing that I've got two pieces of information about. I've got volume and concentration, volume over 1,000 to get decimeter cubed, times by 0.6 moles per decimeter cubed, gives me my moles of HCl, 0.01638. And it so happens, from that equation, that I know that they're a 1-to-1 ratio. That means there is 0.01638 remaining. So I've written that down to remind me that that is the moles of sodium hydroxide in the flask. So that's what was left after the sodium hydroxide over here reacted with the ammonium sulfate over here that was added to the beaker. So I have full information about the sodium hydroxide in the beaker as well. So I can work out how many moles of sodium hydroxide there were in that beaker before the ammonium sulfate was added. So the original moles is going to be 100 centimeter cubed divided by 1,000 to get decimeter cubed times by 0.5, and that gives me 0.05 moles. So that's the moles before the ammonium sulfate was added. And then on the right hand side, we've worked out the moles of sodium hydroxide after the ammonium sulfate was added. So we can work out how many moles of sodium hydroxide reacted with that sample of ammonium sulfate. It's just going to be the moles that I had minus the moles that I've got remaining in the flask, and that's going to give me sensible numbers all around. So look at these numbers, they are in a similar magnitude. So I haven't got like 0.05 take away 0.000035. The numbers are sensible. That's how people do practicals. They don't do practicals so that one of the moles is 10, 15, 20 times the other. So that's my moles of sodium hydroxide. I now need to use the balanced equation, taking into account that you need 2 moles of sodium hydroxide to react with 1 mole of ammonium sulfate. So my moles of ammonium sulfate, I've changed to green pen. This is my Victory green pen that I use when I'm getting near to the end of a calculation. So that's the number of moles of sodium hydroxide divided by 2 gives me my moles of ammonium sulfate. If I then wanted to know mass, which we're just suggesting in this question is the case, then I'm going to work out my MR of ammonium sulfate, being careful to take into account the units, not to take into account the units, being careful to take into account the brackets, what I meant to say, and then I'm going to find the mass. So number of moles, 0.01681, I haven't rounded it up yet. I can round it up at the end when I get my final mass value, which is going to be 2.22 grams. A sensible mass to be adding to 100 centimeter cubed of solution. I'm not expecting a huge mass, and I'm not expecting like 0.00 something either. That's when I know I've done something wrong. I'm also going back to the original information in the question. And in fact, I should have done this as we're going along, and I'm ticking off the numbers that I've used. So that's another really good strategy, just to check that you've used everything. I'm also just checking that I used the balance equation. I did, because that's a really easy step that people miss a lot. So check you use the equations, check you use the numbers. Here's another question with lots of numbers. It's actually very similar because we have a base, calcium carbonate, reacted with an acid, and then we're going to titrate the remaining acid. So it's just we've swapped the acid and the base around. So I've got some limestone, reacted it with hydrochloric acid. Again, it's an excess, we've got leftover acid. Again, this time we've made it up to a large volume and taken a sample out and then titrated it. That's much more common because normally we don't titrate the whole sample in one go because that means we've got no margin for error. And we want to calculate percentage of calcium carbonate. That always means by mass. So I started with 1.25 grams of limestone. I'm writing the calcium carbonate formula, but obviously it's not all calcium carbonate, otherwise I could just work out, I know the mass of that, so that wouldn't help me. So again, I'm writing down what I'm adding it to. I'm adding it to HCl. I've got a volume and a concentration. It says all of it reacts. I'm going to write down an equation for the reaction. This time it's not 1-to-1, well it wasn't previously either. I know it's not 1-to-1 because calcium is in group 2, which means it needs 2 chlorines to make CaCl2, to make the salt. This is an acid-base reaction. But I don't actually need to write all of that out. So I'm actually just going to rub out the right-hand side just because it's going to get in the way. And actually all I need from that equation is the relationship. Calcium carbonate reacts with 2 moles of HCl. So if you do have a balanced equation, you don't necessarily need to write all of it out. You just need the ratio from it. So there's my volumetric flask. This is to remind me that I'm taking that sample and I'm diluting it down. Diluting it won't make a difference to the number of moles, but it means I'm not titrating the whole sample that was in the beaker. This is fairly normal, that I would make up a large volume and take 1/10 of it out. It's how our apparatus is kind of set up. So we'd pipette out 25 centimetre cubed. Then we're going to titrate it using a burette, and in the burette we've got sodium hydroxide. It's 0.1 moles per decimetre cubed, and the volume required was a very suspiciously even 30 centimetres cubed. Doesn't normally happen like that in a titration. This time it was. So, same thing we did before, working backwards. Start always with the information about the concentration of the volume, the thing you know. Again, we weren't given an equation. I know that it's 1-to-1. It's the same equation we were looking at in the previous example. 1 OH minus reacts with 1 H plus. So my moles of sodium hydroxide, it's just going to be 30 over 1,000 to make decimetre cubed, times by 0.1, and that gives me a number in standard form, and it is perfectly fine to just leave it in standard form in your calculator. You're much less likely to make errors if you stop trying to keep changing it in and out of standard form all the time. That's the same as the moles of HCl because of the ratio in the equation, but notice I've also written moles of HCl in 25 centimetre cubed. That is to remind me that what I've just calculated, I've only done the moles of hydrogen chloride, hydrochloric acid, that are in the flask. So this is only the sample that was taken out of this large flask, which is only 1/10 of the volume. So in the large flask, which contains all of the moles of HCl that were in the beaker, we need to times it by 10. So actually there's 0.03 moles of HCl in the volumetric flask. We can also work out, like we did before, how many moles of HCl we had in the original beaker. And that is 0.05 moles. It's an easy calculation. And because we have such nice round numbers, it's now quite easy to see how many moles of HCl reacted when the calcium carbonate was added. So 0.2 moles, 0.05 take away 0.03 is how much reacted, and it reacted in that equation there between calcium carbonate and hydrochloric acid. So I now have a molar ratio. I know that 0.02 moles of HCl reacted, which means that in my original sample of limestone, I must have had 0.01 moles of calcium carbonate. So I'm nearly at the end of my calculation, which of course means that I'm probably going to switch over to my Victory green pen. I've got 0.01 moles of calcium carbonate in the sample, and the sample weighs 1.25 grams, and that's not pure calcium carbonate. So I'm now going to work out the percentage by mass. If I'm going to do anything in building mass, then I need to work out the MR, which is 100.1, and then my mass is therefore going to be my number of moles multiplied by the mass of 1 mole, which is going to give me 1.001 grams. Again, I'm not rounding it up. It's not going to make a huge difference to my percentage, so I may as well leave it as it is for now. Percentage by mass, therefore, is just going to be how many grams of calcium carbonate I've got divided by the mass of the whole sample times 100, and that's going to give me a sensible number of 80.1%. I'm expecting it to be, a large number, large percentage, because it's limestone, and limestone should be mostly calcium carbonate. I'm not expecting it to just be like 2% or 8% or something like that. So I've got a way of self-checking. So what did I do? I could also go back to the question and I'd be ticking off the numbers as I go along, especially with a titration question and especially with a back titration where you're given more than one volume. Just make sure you've used them all. It's quite rare that you don't need to use anything. Sometimes if a substance is in excess and we're not calculating how much of it reacted, we can ignore something that's in excess sometimes. But most of the time we need to use all the information, including the balanced equations that are given to us in the question. So that's something to go back and check. So tomorrow you're going to have some good examples of this. In the meantime, just think about how you can incorporate using diagrams, drawings, flow charts, anything that kind of gets you through a long, wordy calculation and helps you to pick out the practical details.